in question 3. This is our sequence in question 3. We have 1 plus 2 over n to the power of 1 over n. And we will use the same idea again. We will look at the corresponding function for this sequence. So we would define fx to be 1 plus 2 over x to the power of 1 over x. Once again, you see that by restriction to the natural numbers, if you take x to be a natural number n, you would get back the original sequence. And there is no problem here for such a sequence because n is the natural numbers will always be greater or equals to 1. But here we need to be careful because x can be a real value, a real number, and this is going to be defined only for non-zero real numbers. But because we are only interested in natural numbers, so n is always positive, well, we know for sure that this function is always defined when x is greater than 0. Now I want to fix the problem which comes from the power of 1 over x here. I would like to get rid of this power because it's hard to deal with. How can I take this power and sort of shift it down? Well, the way to do this is by means of the logarithm. The logarithm always allows us to bring the power down. So we have to introduce the logarithm here, but to get back f of x, we also need to apply the inverse of the logarithm, which is the exponential function. In other words, using function composition, the exponential of the logarithm of this bit is the same thing as my fx. Once we have the logarithm here, then we can take the power 1 over x and bring it down, and we would have this expression. Inside the exponential, we have brought down the power 1 over x, and here we would have the rest of the expression, ln of 1 plus 2 over x. In order to understand our sequence, the limit of this sequence, once again we study the corresponding limit as x tends to infinity. So we have to apply our limit laws carefully. We note here that, okay, the exponential function is continuous on the whole real line. So we could make the limit commute with the exponential, or we could push the limit inside the exponential, provided that we know that the limit on the inside does exist. For whatever is on the inside, we need to be careful because the logarithm function, it's only going to be continuous when x is a positive real number. So what we will do is to compute the limit of the expression on the inside. So let us compute this limit. As we take x towards infinity, you can see that of course 1 over x is going to tend towards 0, and for this bit here, ln of 1 plus 2 over x, we see that 2 over x is also going to tend to 0, and therefore it's always going to be a positive number. It's always going to be part of the positive real line. 1 plus 2 over x, and you're sending x towards infinity. So you can assume that x is going to be, well, positive throughout. That's an assumption that is reasonable because x is tending towards infinity, so eventually our values of x, which would be put into this formula, will always be large and positive. So what we see therefore is that whatever is on the inside is going to converge to 1. seeing that this converges to 0, 1 plus 2 over x converges to 1, and ln of 1 is going to be 0. So we have that the limit in this case is 0 times 0, and therefore equals to 0 by applying the limit laws correctly. Therefore, this limit does exist. And since we know that the exponential function is continuous on the whole real line, we use that to see that we can certainly take the limit and make it commute with the exponential. We can push it past the exponential so that it becomes the exponential of the limit of whatever is on the inside. And we know what the value is. It is 0. So the limit of this expression is the exponential of 0, which is just 1. And as we noted earlier, this limit is the same thing as the limit as x tends to infinity. Therefore, by restriction to the natural numbers again, and that shows us that the limit as n tends to infinity for fn for the natural numbers is the same thing as the limit for the function f of x as x tends to its infinity, and it's the same thing as this value which we just found. It's just 1. It shows us that in this case, okay, we now know that the sequence has a limit and it converges. The limit is precisely 1. That settles question 3 for us as well.